interested in doing solar physics with the big telescopes in the next 10 years? Well, you already were inclined for that anyway. I think the HST is I mean, this is the first thing we've had on the ground since 1967 or so in the United States. That's a facility, not faculty, instrument. And so, you know, the potential for groundbreaking observations of importance to large Reynolds numbers, magnetized astrophysical systems is really enormous. But it requires, I would hate to think that people just go and use this thing and say, oh, well, here we looked at a model and it changed and it did this, and we have this event that did this and that and the other. No, I'd love to see them address physical questions. And solar physics sometimes is a bit short of that. All right. So the last part of what I'm going to talk, yeah. Right. Yeah. No, you're completely right. But Hinode is the only one with a spectrograph. This one uses a series of filter instruments to choose the wavelengths, and unfortunately, it doesn't have enough filter wavelengths to properly get at the vector field in a way that is safe. You have to measure, remember the Stokes V is first order in the wavelength when you differentiate the line profile. And the more I differentiate a profile, the more resolution I need to see it. So if I take the second derivative of a line profile, I end up with a positive, a negative, and a positive all in the space of the line profile. In the first derivative, I get a negative and a positive. If I take the third derivative, I would get another node. So I get higher and higher Fourier components in the derivatives arrive as I differentiate them more and more. What this means is that HMI does not have the resolution properly to resolve the second order terms, the Q and U parts. So I would use it as a longitudinal magnetogram perfectly fine. I wouldn't have any problem with that. We're using it as a full-blown vector magnetograph. And I believe it serves the purpose of the first thing I talked about, which is, you know, observing the whole sun all the time and trying to measure the things like the magnetic helicity. That kind of thing would be really interesting if you could do it with HMI, and I think you might get away with it. But I would never analyze HMI alone. I would always want to do it with, say, Hinode data of the same region at the same time, because the Hinode data tells you the ground truth, because you don't really have the spectral resolution to do what you need to do. That's a really good question, actually. Any more questions? We have coffee in half an hour, so we can all kind of cheer up. Okay. So what I'd like to do now is, I want to show you some dirty laundry. You know, as an expression in English, you don't show people your dirty laundry in public. I mean, that's just not what you do. Even in Italy, they hang up their laundry, but it's clean, right? They're not going to hang up the dirty stuff. Right. So, but what I want to do is the dirty laundry is the stuff that people don't tell you and is not really, not even really very much discussed. But there are a couple of papers, and I'm highlighting these, and I put them on my website, which I pointed out to you earlier, by Gene Parker and by Hank Sprout, both Hale Prize winners. I mean, Gene Parker is probably arguably the best solar physicist in the second half of the 20th century. In the first half, you could make a case that it was George Ellery Hale. I mean, these are, you know, fantastically talented people. And what they've done is point out some unpleasant truths, some inconvenient truths. If you remember the flawed election that allowed the Supreme Court to select G.W. Bush instead of Al Gore. Al Gore went ahead and talked about the inconvenient truth, and there's some inconvenient truths about the sun that I would like to bring up, and I'm glad that Fausto and Ronnie are here, because if you guys don't complain, then they certainly will. Okay, so I'm going to talk about, as I said, some critical problems. What I mean by this is, I don't want to go around nitpicking and saying, oh, well, I don't believe that, the corona is static because I see moving, therefore all static models are crap. What I'm trying to find out is if there are some really critical observational facts which really challenge the essence of some kind of models of the sun. Is there something about what's going on inside the sun that seems to make sense in terms of MHD modeling, but in fact, when you look really painfully closely at it, there seems to be some kind of issue here. I'll try and express some of those. And what I'll talk about are the following things. And I want to remind you of these things. So those are the two papers I was talking about. And then there's Gene Parker's very nice Conversations on Electromagnetic Fields, which passed around. Remember I started off with talking about Macbeth, and at the end, Chapter 8 of Parker talks about properties of this Maxwell stress tensor. And that might sound rather a esoteric sort of title, but what it is really fundamentally saying is MHD is fatally flawed in the same sense that Macbeth's character is fatally flawed. It leads to his own demise. So he's arguing that MHD basically leads to its own failure, ultimately. And that while there are problems that certainly can be addressed within the realm of MHD, there is an aspect of it which the fatal character flaw built into the system of equations themselves essentially leads to its own demise. Okay. So just to remind you, the big questions I think in solar physics are as follows. Why does it do these things? In particular, Parker has been on for quite some time about, we can certainly imagine a 22-year cycle coming up. We, after all, have some helicity arguments as to how we can go from something that looks like it's symmetric to breaking the symmetry and thereby allowing us with alpha squared effects, the alpha dynamo, or with something else like an alpha omega dynamo, which I'll talk about, can lead to a 22-year cycle here. And so the idea of a varying magnetic field is perhaps not that difficult to understand right now, but why it should do it, if we believe it does it, in the form of sunspots, a concentrated loop of stuff, it's like, instead of a diffusion equation generating a sort of mass of flux all over the sun that evolves with time, this is generating tight bundles of it, and it's emerging through the surface every 11 years in a very strange kind of way. And then, why would the sun and the stars choose to do the following? The order out of chaos thing, I think, has a broad answer from the linkage between the small scales and MHD, namely the kinetic helicity, converting the magnetic helicity, and then giving you an inverse cascade, so you get a large scale out of a small one because of the broken symmetry and the motions on small scales. This is just recapitulating the questions I had earlier. The magnetic field changes ridiculously fast. I mean, in the lifetime of the sun, it's gone every 11 years. If it's done that for every 11 years in its lifetime, it's 4 10 to the 9 years old. It's not difficult to figure out. That's 100 million times it's done this. So I was very amused to read in the news about 6 months ago where a prominent scientist from Lockheed was quoted as saying, oh, yes, the sun's going to change flip its polar field in the very near future, and people are like, oh my God, we're all going to die, Martians are going to invade, and all these terrible things are going to happen, the electrical grid's going to go down, they'll have rats evacuating the United States into the oceans and all kinds of good stuff. Well, it's only done it 10 to the 8 times before, guys, it's, so what? Anyway, but it is remarkable. This is like an organism like me, just going round and round all the time, all my life. I mean, that's all I do. I mean, it just doesn't make a lot of sense in some bizarre overall scenario. So, and then another thing is, the magnetic field changes almost instantaneously. I mean, it can't change much faster than something called the Alfvén speed, but, why is it obliged to actually do this? I mean, why should it ever produce a flare? Why should it ever produce a CME? And by these things, I mean, why are you taking what appears to be magnetic energy and dumping it out in into the plasma and then radiation? particles, conduction, you name it. And why is it obliged to make these topological changes? Well, as we saw earlier, topology is everything in MHD because you have the advection equation. If it's in a high Reynolds number case, it's a topological problem. And the business of changing the magnetic field comes down to changing the topology. So these are all kind of related. And finally, why are coronae so ubiquitous? Every single star that anybody's ever looked at with enough sensitivity has a corona if it's sun-like. Jürgen Schmidt showed this in '94. There isn't one that doesn't have a corona. So every damn star has to do this. Okay? So let's have a quick look at a dynamo. So I believe Fausto mostly discussed dynamos of this kind, although he didn't put it quite in these terms. So what you do is you take an equation and you generate your mean field equations, and you go through the machinery of it, and you end up with a current that's proportional to, a magnetic field. The change in the mean magnetic field with time is proportional to the mean current density, which is really amazing. What this means is that you're changing from, because you've got a curl of this thing here, this is a change, if you think of it like this, from poloidal into toroidal, and then if you do this more than once, you've gone then from toroidal to poloidal, and then poloidal to toroidal. So here, you have a complete cycle in principle. Okay? Whether this works on a 22-year scale seems unlikely because, in general, you have stationary solutions to this kind of problem. These are slides taken from Matthias Rempel, another colleague of mine. By the way, that's a good trick. If you don't understand the subject very well, you get people much cleverer than you are to help you out. That's a very well-known thing. It's nice to do things yourself and work through them, but I find it very helpful to talk to really, really bright people, and both Roberto and Matthias are much cleverer than I am. That's the other thing. If you ever get in a position of power to hire someone, make sure they're cleverer than you are, right? That's a good thing to do. Okay, so that's the kind of problem that is the alpha squared type. But now let's add in something, and I'm just going to give you an illustration so that I can criticize it later, or look at it with a critical eye. So here, what are we doing? We're looking at the sun's rotational properties in the interior, and we're trying to find out, we're going to look at, remember Fausto was talking about the curl V cross B term in the induction equation being an advection part, a stretching part, and a compression part. So we're going to look at the stretching part here. And so what goes on, what we're going to do here is look at models in which one specifies a phi component of the magnetic field, and then this is the toroidal component going around the axis of the rotating sun, and then this is the poloidal component because it's the curl of the other part, and we've got a scalar A there. Fausto used this formalism in some of his lectures there. But also we now impose on it and look at the induction equation for a given flow, which we will take from the helioseismology. So this is work done by various groups. Dick Party and Charbonneau is one of the first papers I know to do this with the recently discovered internal rotation rate of the sun, et cetera, And furthermore, we're going to see what happens here. So if we just use that, we end up with, in spherical geometry, various terms that control, and remember, we're after dB by dt. That's the thing we're really after. And just by taking a curl, we're after dA by dt. We take the curl of that and we get the same thing. Well, what you notice here is that we have, I'm colorblind, so it's actually kind of difficult to see, but I believe this differential rotation is this term, right? And then, so this is a dissipative term, this is a dissipative term, two independent equations, one of which has no source term. It's advection and dissipation. So there is nothing to maintain, and remember this is the poloidal component, so there's nothing to maintain the poloidal field against ohmic decay. This is the dynamo problem. So we do have something, we have a thing, a grad of omega, grad of the gradient in latitude and or radius, which will generate a magnetic field through this term, and it will work against the dissipation according to this term. I'm not going to talk about what happens when sine theta is 0 here, okay? Because I don't know what you do with that. What is the omega effect? Well, this is the one. This is this term here. if we take the rotation profile somewhere in the interior of the sun, it takes a poloidal field and it stretches it around like this, and then, like magic, bang, something happened to change the topology there, and that, of course, is reconnection, right? So just to run that again, there's the original field, and now we're generating fields, and you'll notice that the direction of the field is opposite for the same initial poloidal field. It's opposite in the two hemispheres, which is good, because if that's really going on, remember the sunspots emerge with positive and negative polarity in one hemisphere and the other way around in the other one. So, you know, flux rope kind of picture looks pretty good. Alpha effect, what's that? So here's this sneaky thing where you try to walk out from the middle of the sun and you get turned around on your way through. So here's the alpha effect. And here we have a cartoon of, you know, what happens. There's the omega. So now we're converting the toroidal field into poloidal field. Yeah. Okay. So in principle, we can complete a cycle here, and that's done through this term here. And these are empirical terms put into these equations, which are of kinematic type. So what you're trying to do is not solve the full set of dynamo equations. You're trying to just see if this produces some kind of dynamo compatible with what they observe on the sun. Can you make it work? Well, the first thing you notice is that these have properties of cyclic behavior. That's really important. I mean, 50% of stars show cycling behavior of solar type. So at this point, we keep this in mind as a potentially important kind of model that we want to use to describe the evolution of the sun's dynamo. And what we've done here, all we've done is taken the differential rotation, and we've taken some of this kinetic helicity and used it as a source term to drive the toroidal to poloidal version of the field. And there are several classes of models which were totally trashed, not allowable by the measurements of the interior properties of the sun using helioseismology. And of those, a couple of them really have survived. One is called an interface dynamo, which operates down here. Another one is called a dynamo of a Babcock-Layton type. And that just specifies where and how you deal with this alpha term and what you do with these diffusivities relative to those alphas. Okay? So the details I don't want to get into, you can find them in the literature easily enough. These models are, in quotes, successful. Here is a picture of the radial field. Solid line is plus, dashed line is minus, solid line is plus. So it changes sign every 10 years or so. Sorry. And what's going on here is that this is a latitude, so this is the equator, so this is one hemisphere, and in that hemisphere, one gets a bunch of positive field generated at around 30 degrees, 40 degrees, and it migrates towards the equator. This is compatible with what we know about the sun. But in a way, if it weren't, we would have set up our calculations incorrectly, because we've got the freedom to specify some parameters of this model, and they've been adjusted to work. In particular, one of the ones that's been specified is this turbulent diffusivity, which Fausto, and we'll get back to that later. But if we used an ordinary diffusivity here in a laminar kind of flow, which it's not, and Fausto argued quite forcefully, I think, that in a high Reynolds number flow, you're going to end up with turbulent diffusion no matter what you try and do. So this is perhaps not unreasonable. But if it were a laminar thing, you know, we would be off by 8 orders of magnitude, just to give you the idea. This is 8 orders of magnitude larger than a kinematic thermal diffusivity. Okay. Okay. So the interesting thing is, so there is some success in this modeling. You get diffuse patches of field which migrate towards the thing, change sign every 11 years, migrate towards the equator. But you also saw those things going towards the pole. That also is found in the dynamo, in the observations. So this dynamo The question is, it's not an ab initio calculation. It's not even dynamic. It's kinematic. So you have to ask yourself, what has it really gained us? Have we really learned something? And the way I think about this is, we'd better investigate something about the reality of this thing to test whether we're really understanding what's going on. For instance, as well as some of the other assumptions, like how they prescribe the velocity field on the surface of the sun and in the interior. And this particular class of model is a flux transport model in which you put the alpha effect close to the surface, and then you use the meridional circulation. I mean, the meridional circulation is a natural thing that happens in rotating bodies in which you have some forcing, small amount of forcing, and you naturally get these circulation cells along the meridians of the fluid. And so there are several assumptions built into this thing, and I'm going to look at the one to do with turbulent diffusivities just for the heck of it. But the success of that, you need to keep in mind, as I said at the beginning, what are the critical tests of these things? And does anybody want to, I think you probably know, those solar physicists of you know where the sun is going to be on a plot like this. What is this? This is a plot of the rotation period of the star, of a given star, as determined from, you take a light curve, you take the Fourier transform, and you look for the sort of fundamental lowest frequency at which things are going on a period of about a month or less. And you end up with, and that's what this corresponds to, is the passage of sunspots across the disk of the sun, or the star, or plage, or something, okay? So, and then what you look at is you wait for 25 years, and you keep taking data. So you just take a bunch of time series. On this axis is the fast component of the variability to do with the rotation. On this is whatever you can find in the way of cycles on stars. And it turns out that these guys fall into two branches. The sun has a rotation period of what? 27 days. So the sun's going to be in here. And what's its cycle length in terms of what you would see if you observed it as a star without being able to measure a magnetic field? 11 years. So what we've done is we've successfully constructed a dynamo which works for the sun. The question then arises, so what we've done is we've got bells and whistles, we can adjust them and make them fit the sun, and if we're only solar physicists and don't know anything about stars, we'd be perfectly happy. I show my colleagues this, and they don't know what to do. I tell them, no, what you've done is you've managed to construct a star with enough free parameters which behaves like the sun. You need to just construct something that will produce something in which the sun behaves in the context of the other stars. Now, this is a fairly small population, but the statistical difference between these guys and these guys is enormous. I mean, there's no way around it. The probability of those being drawn from the same distribution is nil, 10 to the minus 30 or something. And the sun is set squarely in the middle. So this is another pet peeve of mine, is we should never, ever consider looking at the sun alone. And if we want to understand the dynamo, we've got to explain this. And anybody tells you they think they understand how the sun's dynamo works, you show them this and ask them, what the hell is going on, guys? Well, the stellar data are wrong, the periods are all wrong, we're looking at overtones, we're looking at this, that, and the other. No, I don't think so. Time will tell, because after all, it takes a long time. This is a bit longer than an average PhD thesis takes, 25 years. Thank goodness. But, if you keep measuring these damn stars, these boring telescopes, how bright they are and how they change with time, and you just keep doing it, and you allow, old people with, old detectors to keep doing this and give them a little bit of money every so often, keep them happy, we're going to end up with very, very long databases here. And so this leads me to emphasize one more thing. Funding agencies operate on timescales of 2 years if you're lucky, 3 if you're really lucky, 5 years if you're, won the jackpot or something. That's got nothing to do. The stars don't know anything about those timescales. Nothing. And so it takes a concerted effort on the behalf of scientists to decide that, you know, we need to do research in a certain area for very long periods of time, and we need to make it attractive to people without promising them instant gratification. Modern society is all about instant gratification. You know, the moment I go home, I start logging on and looking at BBC and all this stuff. It's instant information, right? This kind of science doesn't work like that. And so the reason I'm bringing it up is, you know, while things like SDO have lifetimes of 3 years for $1 billion, what about $1 billion worth of stuff for people to work for the next 100 years with a few more telescopes around the world? That would be pretty nice, right? That's never going to happen because you can't make pretty pictures of flares going off and advertise it on space news and all this other stuff. So it's up to the scientists to decide to do boring science. And to hell with the people that want us to do exciting, wonderful pictures. To hell with them. That's not science. This kind of study, I would like to see this graph extended. I would like to know what the longest period ever detected of a variable, a star like Sun would be in comparison. It seems to be proportional to the rotation period. So find some really slowly rotating stars and see how long they go. I mean, let's do this, you know. But it's not easy. Okay, we've got a couple of minutes. Okay. I'm going to have an hour to talk about this, so let me finish up this part with a quick discussion of reconnection. Now, reconnection is sort of what Yoko, what Solar B, Hinode, what the Japanese are fascinated by, obsessed with. I mean, it's like, you know. And the reason is high magnetic Reynolds number topology. What's reconnection? It's just changing the topology. That's my feeling of what it's all about. In the dynamo simulations, this is all due to a turbulent diffusion. But reconnection is actually a dynamic process involving forces. And we haven't addressed the forces if we use a turbulent diffusivity, at least not directly. That's all to do with correlations between velocity and magnetic field without looking at the momentum equation. So we better make sure that we understand that this thing is a valid concept in terms of dynamics. What happens if you don't have reconnection? This is a driven simulation of what happens. These are field lines, and what they've done is essentially just let this thing sit there, and then they start twisting up the foot points of this thing, and you generate helical structures, and it goes off into amongst. So this is a box with magnetic field. It's got infinite Reynolds number. There's no diffusion here. It's just a calculation along the field lines. So you track the field lines in a Lagrangian sense. You don't actually solve the MHD equations, but it's but this is what would happen, right? You just twist and twist and twist, and nothing interesting happens. You just sort of emerge this twisted bird's nest into a place. Things like this are just not seen in the sun. This kind of complexity, even in the most extreme cases of twisted-looking prominences and stuff like this, which you can find, I don't believe they're quite as complex as this. Something has happened to stop that happening. And that thing that happens is that the RM, while it's very large, is not infinite. And so some field lines have been cut. Okay. This is a different picture about than what Fausto was talking. A different way of looking at the same kind of thing. Stretching field lines. So you just pull them and stretch them like taffy. Twisting, folding, reconnection. In order to go from an initial state to a final state where you have doubled essentially the magnetic field strength by doing this process, something has got to happen in here to snap this thing here. We don't have to do it all the way along a huge length. We only need to snap it off in one place to make it work. And so the topological problem is kind of interesting because it's a way of looking at the evolution of magnetism in very high magnetic Reynolds number systems. And you can draw diagrams like this which reflect what is a dynamo. I mean, here you've got motions which are stretching. That's the differential rotation, if you like. Twisting, that's the alpha effect. And then you get something like this, but you must have the reconnection to make this thing work. Okay? Let's look at what is going on. If we have a magnetic field such that it looks like this, we bring two loops close together like this, just like in the flare model I showed with Shibata. You bring them close together. What's going to happen? Well, in this case, you can figure out that the Lorentz force on this part of the magnetic field is up, and the Lorentz force on that part of the magnetic field is down. This is a kind of dynamically driven system in which if you happen to bring two field lines of opposite polarity together, they will attract each other. And so, again, I'm just going to refer you to the literature, but I just want to point out the difference between slow and fast reconnection. And it's essentially to do with how long this thing is. So imagine having a big old current loop, magnetic loop above this thing and a big old one underneath it, and then folding them over and bringing them together. And we want them to reconnect to complete this cycle to make double the magnetic field strength. Then what would we do? Well, in what they call a Sweet-Parker model, you would use the continuity equation, V times Lx equals the alphane speed out times the thickness. To derive, together with another equation, you would end up with an expression that looks like this. We get this Rm to the half again. If Rm is 10 to the 14 in the sun, Rm to the half, that's a pretty slow reconnection rate. Rm to the half is 10 to the 7, so we've got a very small one. But if somehow we can bring these together without having to make this whole length squeeze together and diffuse, if we can make them much shorter, and Petschek did it in 1964, again, there's this wonderful proceedings I mentioned on Monday, 1964, then we can make it happen much faster. And you end up with something that looks like a logarithmic dependence, essentially independent of the magnetic Reynolds number. You go from 10 to the 14 to 14. Well, great. There is another kind of picture in which people have argued is fundamentally different, but I don't think it really is. They just invoke turbulence. So you say, well, you have ridges in this thing, therefore the lengths of contact are not on this scale, and therefore we can end up with very fast reconnection of this kind simply because of that. There are furthermore other kinds of pictures. Oh, there was another one. There it is. In which people talk about you go beyond the MHD approximation and actually use various plasma instabilities and plasma wave particle interaction, what have you. It essentially amounts to the same thing. That for whatever reason, it all amounts to the same thing, namely that we have fast reconnection going on. And then we'll start again after the break. Okay? Coffee time, right?